Please like, share and subscribe our channel to learn and enjoy our free online educational videos from class nursery to 10. Please click the bell icon to get all new updated videos.
Lesson 1. Real Numbers. Introduction. We know that all rational and all irrational numbers make the collection of real numbers. It is denoted by the letter R. In this chapter, we begin with two very important properties of positive integers, namely the Euclid's division algorithm and the fundamental theorem of arithmetic. Euclid's division lemma. For given positive integers a and b, there exist unique whole numbers q and r satisfying the relation a equal to bq plus r, 0 less than or equal to r less than b. It is basic concept and it is restatement of division. A is called dividend, b is called divisor, q is called quotient, r is called remainder. If remainder r is equal to 0, then b is divisor of a. Example, for 11 and 2, 11 equal to 2 multiplied by 5 plus 1. For 10 and 2, 11 equal to 2 multiplied by 5. Euclid's division algorithm. This is based on Euclid's division lemma. According to this, the HCF of any two positive integers a and b with a greater than b is obtained as follows. Step 1. Apply the division lemma to find q and r, where a is equal to bq plus r, 0 less than or equal to r less than b. Step 2. If r equal to 0, the HCF is b. If r is not equal to 0, apply Euclid's lemma to b and r. Step 3. Continue the process till the remainder is 0. The divisor at this stage will be HCF AB. Also, HCF AB equal to HCF BR. Example. A sweet seller has 420 Kaju Barfis and 130 Badam Barfis. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. What is the number of that can be placed in each stack for this purpose? Solution. We find HCF 420, 130. Then this number will give the maximum number of barfis in each stack and the number of stacks will then be the least. The area of the tray that is used up will be the least. Now let us use Euclid's algorithm to find their HCF. We have 420 equal to 130 multiplied by 3 plus 30. 130 equal to 30 multiplied by 4 plus 10. 30 equal to 10 multiplied by 3 plus 0. So the HCF of 420 and 130 is 10. Therefore, the sweet seller can make stacks of 10 for both kinds of barfi. The fundamental theorem of arithmetic. Theorem 2. Fundamental theorem of arithmetic. Every composite number can be expressed, factorized as a product of primes, and this factorization is unique, apart from the order in which the prime factors occur. This method is also called the prime factorization method. The prime factorization of a natural number is unique, except for the order of its factors. Fundamental theorem of arithmetic. Circle the primes as they appear. Prime factors 2, 3, 2, 7, 13. Revisiting irrational numbers. The number s is called irrational if it cannot be written in the form of p over q, where p and q are integers and q is not equal to 0 or in the simplest form. The numbers which are not rational are called irrational numbers. Example, under root 2, under root 3, etc. Theorem 3. Let p be a prime number. If p divides a square, then p divides a, where a is a positive integer. If p is a positive number and not a perfect square, then under root n is definitely an irrational number. If p is a prime number, then under root p is also an irrational number. Theorem 4. Under root 2 is irrational. Proof. Let us assume to the contrary that under root 2 is rational. So, we can find integers r and s not equal to 0 such that under root 2 is equal to r upon s. Suppose r and s have a common factor other than 1. Then we divide by the common factor to get under root 2 equal to a upon b, where a and b are co-prime. So b under root 2 is equal to a. Squaring on both sides and rearranging, we get 2b square equal to a square. Therefore, 2 divides a square. Now, by Theorem 3, it follows that 2 divides a. So, we can write a equal to 2c for some integer c. Revisiting rational numbers and their decimal expansions. Numbers which can be written in the form of p upon q, q not equal to 0, where p, q are integers, are called rational numbers. Note, every terminating decimal and non-terminating repeating decimal can be expressed in the form p upon q, q not equal to 0. Example 1. 0.27 is equal to 27 upon 100 is equal to 27 upon 2 square multiplied by 5 square. From the above examples, we notice that every rational number of the form p upon q, q not equal to 0, where q is of the form 2 to the power n multiplied by 5 to the power n, can be written as x upon y, where y is of the form 10 to the power k, k being a natural number. Theorem 5. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p upon q, where p and q are co-prime, and the prime factorization of q is of the form 2 to the power n, 5 to the power m, where n, m are non-negative integers. Example 3 upon 8 is equal to 3 upon 2 cube is equal to 3 multiplied by 5 cube upon 2 cube multiplied by 5 cube is equal to 375 upon 10 cube is equal to 0.375. Theorem 6. Let x equal to p upon q, where p and q are co-primes, be a rational number such that the prime factorization of q is not of the form 2n 5m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating, recurring.